Hi, Christin Bibby from Louisiana State University. Christin will talk about supersolvable posets and fiber type arrangements.
All right. Thank you. Thanks to the organizers for the opportunity to speak here. So this is joint work with Emanuele De Lucchi, who's based in Switzerland. And it's a story about something purely combinatorial, these supersolvable posets, and something that's very topological, fiber type arrangements and the connection between them. And it'll be a while before I get to what those words mean. I want to start with a motivating example, which is maybe a little bit closer to what a lot of you work with. So a configuration space is a collection of n tuples of points in your favorite space X, where no two of those points are the same. So n tuples of distinct points in X. And for what I'm going to say next, I want my space X to be a nice manifold. And one really important tool in studying the topology of these spaces is a structure of a fiber bundle. So there's a way of taking a configuration of n plus 1 points and forgetting the last point, and this gives you a configuration of n points. And this is a perfectly nice map, but what's special about it is that if I look at any configuration downstairs, so if I have n distinct points, all of the things that sit above it in the fiber are all of the ways that I can add this extra point that is not the same as those n that I already started with. So you can easily see that the fibers are all the same. They all are just x minus n points. But moreover, this has the structure of a fiber bundle. So there's actually a little neighborhood of this where this is a trivial bundle. And this tool is used to study a lot of the topological invariants of these spaces. So I'm going to list a few of these. Or really the first thing I'm going to say, so this is going to be in the case that x is equal to c. This is particularly interesting because its fundamental group is a pure braid group. I drew a little picture up at the top of an example of this, kind of time equals 0 at the top down to t equals 1 at the bottom. You can imagine a configuration of 3 points here. They can move around the plane, but they're never allowed to collide. So you get these little pictures of braids. And one thing that you can see from the fiber bundle directly is that all of the higher homotopy groups vanish. So when you have a fiber bundle, you get a long exact sequence in the homotopy groups. And the fiber, in this case, C minus some number of points, has the homotopy type of a wedge of circles. And you can use an inductive argument to say that, well, the fiber I know is homotopy equivalent to a wedge of circles, so it has no higher homotopy groups. The base by induction has no higher homotopy groups. So in the middle, we can't have any higher homotopy groups. So these are k-pi1 spaces. And this also gives us, so all of the higher homotopy groups vanish, but then when you look at the fundamental groups, we get this short exact sequence, and there's actually a section of the bundle that makes this a split short exact sequence. So you can build up the fundamental groups of these as iterated semi-direct products of free groups, the free group coming from the fiber. You can also say something similar about the rational homotopy groups. And when looking at the cohomology, another thing the fiber bundle gives us is a tensor product structure on the cohomology rings. So if you have a fiber bundle, you can use something like the Serre spectral sequence to try and compute cohomology. And this is like the best case scenario where this local system in the fiber is trivial. And you can really just write the cohomology of the total space as the tensor product of the cohomology of the base and of the fiber. And if you look at just the dimensions of these, and so let's say this is with rational coefficients and count the dimensions of them. And with the Poincare polynomial, this tensor product structure breaks up into writing this Poincare polynomial as just a product of linear factors, where this coefficient is counting the number of points in the fiber at each step. And something a little bit more modern is you could also look at what happens as n increases. And the symmetric group acts on these configuration spaces by permuting the points. And so as n increases, you start to see the same representations of the symmetric group. Okay, so there's a lot of other really nice things that we can say about the topology of these spaces. And really the reason why we can is because of that fiber bundle structure. And that fiber bundle structure exists because of some underlying combinatorics. So I want to say where this combinatorics comes from, and it's from viewing this configuration space as the complement to some collection of submanifolds. So here I can think about the configuration space, which contains n tuples of distinct points, as being the complement of all of these spaces where two points are the same. So these are kind of these bad configurations, these diagonals. So every point in this complement must then have distinct points. And the way that these diagonals intersect each other is where the combinatorial structure is coming into play. So over on the left I have, so let's look at all of the intersections of these diagonals. And I'm going to view it as a partially ordered set by reverse inclusion. So the picture that I drew here is that I have, so this is the case that n is equal to 3. So I have my ambient space, all of this is sitting inside of X3. Each of these diagonals, so this is where the first 2 points collide, this is where the first and third do, and where the last 2 points collide. But then if I intersect any two of these, so if I intersect these first two, I'm requiring the first and second to be the same, and the first and third to be the same, and that's really forcing all three to be the same. So any two of these or all three of them intersect at this submanifold where all three of them are the same. And the way that I've drawn this picture is that these lines denote inclusion. So each of these diagonals is contained inside of the ambient space, and this subspace is contained inside of each of these three. But we can describe this purely combinatorially by looking at partitions of the set 1 through n. I can think about one of these intersections as putting some equivalence relation on the indexing set. So here, x1 and x2 must be the same. So this corresponds to a partition where 1 and 2 are equivalent to each other, and then 3 is all by itself. And same here, this is forcing 1 and 3 to be equivalent to each other, and 2 by itself. And up at the top, 1, 2, and 3 are all equivalent to each other because all 3 coordinates are equal. Okay, so this has a lot of nice combinatorial structure. And so really the question that I want to explore is, when do we get similar kinds of fibrations? So what if I look inside of some x to the n plus 1, remove some kind of bad subspaces, and look at the complement of that? And when can I restrict there and get a nice fiber bundle? And in particular, can I describe this combinatorially using some sort of intersections among these subspaces? Okay. And there's a couple of variations on configuration spaces where we can see this happening. The first is a partial configuration space. So here, instead of requiring any two points to be distinct, I'm going to loosen this a little bit and let it be determined by a graph. So here I'm going to make sure that xi and xj are distinct whenever I and j are an edge of my graph. So the complete graph has all possible edges, and this is going to force any 2 points to be distinct. But this is kind of another example. So this is a graph with 4 vertices, and here the way this is written is the first point has to be different from the second and different from the fourth, but it doesn't matter because there's no edge between 1 and 3. It doesn't matter if 1 and 3 are the same. Okay, so I can start to ask whether this has a fiber bundle structure. So this sits inside of x to the fourth because it has 4 vertices, and I can ask what happens if I forget the fourth coordinate. So this will go down to now a graph which looks something like this, dropping the 4th vertex. And if I look above a point like this, so this is 3 points, and here the first and second have to be different, the second and third have to be different, but I don't care. I don't have any conditions on the first and third because I'm missing that edge. But if I look at what's sitting above that, what I need to do is add a 4th point, so that 4th point can't be the same as the first, and it can't be the same as the third. So if I'm looking above a point where the first and third are the same, then there's really only 1 point that I have to exclude. But if the first and third points are different, then the 4th point can't be either of those 2 points, so there's 2 points that I have to exclude. So this has different fibers, and so we're not going to get a fiber bundle structure out of this. And the problem was exactly that this fourth point was connected to 1 and 3, but there was nothing connecting 1 and 3. So we can look at a different graph. So this one here is exactly that this fourth point. Now, if I did connect 1 and 3, I will get a fiber bundle structure. Forgetting that first point, now going into a configuration where all 3 points must be distinct. And what I've drawn here is kind of a sequence of these. So when I started, I talked about this configuration space of n+1 points, forgetting a point to n points, but you can keep doing this and get a sequence of these. And graphs which allow this happen are what are called chordal. So you can start with a graph like this. Vertex 5, it's connected to 1, 3, and 4. And 1, 3, and 4 must all be distinct because they're all connected by edges. So then I can drop 5, I get down a graph like this. Vertex 4, it's connected to 1 and 3, and 1 and 3 are connected to each other as well. So I can forget that one. And then the same thing down here, vertex 3, it's connected to 1 and 2, which are connected. So we're going to get a fiber bundle there. Okay. Okay, so we can characterize when these have fiber bundles by something that is purely combinatorial, this property of being chordal. And I didn't say what chordal actually means. So one definition of chordal is exactly that I can order the vertices in such a way that each vertex is connected to vertices that are all adjacent to each other. But another way where the word chordal is really coming from, whenever I have a cycle, like this is a 4 cycle, that has more than 3 edges, it must have a chord. So this is missing that chord, which this one has. And another case where we can see this fiber bundle structure is for orbit configuration spaces. So this is a generalization where you have not just a space, but also a group acting on your space. And then I'm going to look at configurations of points where they don't necessarily, or where they don't just have to be distinct, but they have to be from distinct orbits under the group action. And this has a similar kind of fiber bundle structure from forgetting one of the points in the configuration. Okay, so the next case, which I'm going to talk a bit more about, is when we choose X to be a connected abelian Lie group. We can use this to define some particularly nice subspaces of X to the n. So what I can do is because I have a group structure, I can take an n tuple of points and use this group operation to pick out some element of X, take like a linear combination of them. So if you're thinking of say, C, like we were before, this is just taking a linear combination of points in C, and then the kernel of this. So if I had C, this is really looking at a map from C to the n to C. This is a linear function, and its kernel is defining a hyperplane. If I was doing the configuration space that we started with, I could take this linear combination to be like xi minus xj. And the kernel of that is exactly that diagonal where xi equals xj. So this is giving me something of a similar kind of flavor. All right. And so what I'm going to do is kind of like with the configuration space, I've viewed it as say C to the n minus a bunch of these diagonals. Here I'm going to look at a collection of these things, so kernels of these maps, a finite set of those, and what I care about is the complement of this. So you should think about each of these as defining kind of bad configurations that I want to throw out, and look at the complement. And these spaces in general, when X is not compact, we can understand the cohomology. But even if I took like S1 times S1, we don't know very much about the cohomology of configuration spaces on that. So there's still a lot that's not known. And so it would be nice to have a fiber bundle structure around to give us a little bit more leverage to try and understand this. And the combinatorics that's coming into play is, again, I want to look at how these guys intersect each other. And I'm going to have some examples on the next slide that show this, but these intersections don't necessarily have to be connected. So I'm going to look at their connected components. So maybe I should skip to some examples, which will be a little bit more enlightening. So here's something a little bit maybe more familiar. So this is just in C2, except here what I've drawn is R2. So these things, so if I looked at, say, 1, 0, this is defining the equation 1 times x plus 0 times y equals 0, or just x equals 0. So this is this line in C2, but I've drawn R2 because I can't draw C2. And if I had 1, 0, this is defining the line y equals 0. And if I had 2, 1, this is defining the line y equals 2x there. So I want to look at, so these are 3 lines inside of a plane, and I want to look at the complement of that. And the combinatorics that's controlling this is a picture like this. This is the same kind of combinatorics that we had for the configuration space. I have my ambient space down here, each of these lines sitting above it, and then they all intersect there at the origin. So my next favorite example is when I take x to be C star. So here we're getting what's called a toric arrangement. So each of these things is going to define a subtorus inside of C star squared. And I can't draw C star squared, so I've drawn S1 squared. So this is the usual square for S1 times S1, where the opposite sides are glued together. And now if I look at this 1, 0, this is going to define, well, C star is a multiplicative group. So this is going to define x to the 1, y to the 0 equals 1. So it's this subtorus inside of the 2 torus, where the first coordinate is equal to 1. And then this is going to be y equals 1. And then this last one, this is x squared, y to the minus 1 equals 1, or y equals x squared. So this is, here it's like a little subtorus that wraps around this torus twice. And if I look at how these things intersect each other, I again have everything is sitting inside of my 2 torus. And then I have each of these, this yellow, then this blue, and then this red guy that wraps around. Each of those is a connected subtorus. And then we can see that these 3 all intersect here at the identity, where x and y are both equal to 1. But the blue and the red intersect here as well. So I get another intersection point there. So kind of one big difference between these two things is when I do have, in the case of C, these posets have a lot of nice structure. They're called geometric lattices, or they're the lattice of flats of a matroid. And over here, we get something that's quite a bit more complicated. So if you look kind of around a little point, so if I looked at this point here, and I just looked in a little neighborhood of it, what I see are kind of a yellow line and a blue line and a red line all intersecting at that point. So in this poset picture down here, I'm looking at the identity, and I look at all of the stuff that contains it, and that little piece of this poset looks exactly like this. So we have this kind of local picture that this locally looks like these lines intersecting. And we can see that in the poset by looking kind of underneath something. But it's a little bit more complicated because we also have this like blue and red here. They intersect in 2 places. So if we look above them, we get these 2 kind of minimal upper bounds. Okay. And one more example that will be useful. So the one thing that I changed here is the first one is a 2, 0. So now this defines on a torus x squared equals to 1. And x squared equals 1 actually has 2 connected components because x equals 1 or x equals minus 1 are both solutions to that. So we get these kind of 2 subtori coming from that one thing. And the difference in the poset picture down here is I have this extra yellow guy coming from that connected component, and now all 3 of these guys intersect at that point. Okay. Questions on this combinatoric so far? So So the question is really when we get these fiber bundle structures. So let's go back to the left. So what I'm doing, so this is sitting inside of C2, and I want to forget the second coordinate, so I'm going down to C. And I want to look at the complement of these three lines. So if I restrict to everything that's not on these three lines, the image of that is everything except for where x is equal to 0. And if I look above a point that's not 0, what I see is all of the ways that I can add a point y so that I'm not on this blue line and I'm not on this red line. So I see that y is not allowed to be 0 and y is not allowed to be 2 times x. But it didn't matter which x I had, it's always going to be, I have kind of a C many choices except for 2 points. So my fibers all look like this, C minus 2 points. All right, again, I've drawn R minus 2 points. Okay. So, right, I hope I convinced you that the fibers are all the same. It's maybe not so hard to imagine that it's locally trivial. If I looked in a little neighborhood here, you get kind of a strip here, and you can imagine leveling out this line so it looks like kind of that little neighborhood times this fiber. Okay. All right, but let's look at these toric examples. So here, if I were to forget the second coordinate, I'm looking again at the complement of all of these subtori of my torus, and I get out of this all possible x's except for x is equal to 1 in the image. So this is mapping down to C star minus 1. And if I look above points, most of the time what I see, if I pick an x out here, then sitting above it, it looks like I can pick any point in C star except for the blue and the red, which most of the time are distinct, except when x is equal to -1. When x equals -1, then both the blue and the red are at the same point. Okay, so we don't get a fiber bundle here because the fiber bundles aren't the same, but on the right we do get it, because this, now if I remove this x equals 1, now I don't have to worry about that bad fiber. Another thing that I could have done, so this picture is that one just flipped, so I swapped x and y. So now instead of forgetting the second coordinate, I'm going to forget the first coordinate. And when I do that, so this sends x comma y down to y, the image of this is everything except for where y is equal to 1. And if I look above any point, what I see now are any C star except for 3 punctures, this yellow and 2 reds. Okay, so this is also going to have the structure of a fiber bundle. So I want to see this combinatorially. So here's kind of the same pictures that we saw in the last slide. Okay, so I want to see combinatorially why these 3 are fiber bundles and this one is not. And really the thing to look for is exactly this kind of intersection here, that the red and the blue intersected at a point that gave me this notably bad fiber. And in the poset, what we see is this red and the blue, they intersect at this point here. That's what we're seeing there. And the problem is that that point is not contained in this yellow. And this is a lot like that chordal graph property that I was talking about, is kind of, we need, like, if I have 2 edges connecting to this new point, they had to have been connected by an edge already. Okay. So we can make this a little bit more precise. So what we're looking for, and maybe I should go back one more thing. So what I've drawn here, so in these posets, what I've drawn is, so downstairs what we see is an arrangement of some things. It's a little bit, it's a small example, right? Because this is just C minus a point. But what I've done is in these posets, I've highlighted the intersection pattern of the downstairs arrangement. So downstairs, so here what we see are 2 points inside of C star, so we see kind of 2 points inside of C star. So this highlighted bit is describing the downstairs arrangement. Okay, and I want to look at how that highlighted bit sits inside of the big poset. And the key property, so to really describe this intersection bit downstairs, what we need is, so it should be downward closed. So what that means is if I have something in there, everything below it should be in there. I'm looking at all of the stuff that contains it. And it has to have this property of being join closed, which means that if I have two things in there, then their minimal upper bounds should also be in there. So something, I guess these two guys, they don't have a common upper bound, so that's fine. But if I had something like this guy and this guy, they have this as an upper bound, and so I would need to include that if I had both of these guys in there. Okay. But the really key property that makes it, that is going to give us these fiber bundles is what gives us what's called an M-ideal, which I need. So here in the poset, I always have my ambient space at the bottom. The stuff right above it, these are coming from those subspaces in my arrangement. In poset language, these are called atoms. So what I need is for these two guys that are kind of in my arrangement, but not downstairs. What I need is if I look at an upper bound of them, a minimal upper bound of these two guys, then it should be sitting above some atom in this highlighted part. Okay, so that's why this one is not, because these two guys, they intersect at this point, which is not contained in this yellow guy. But it's fine for something like this, because the red and the yellow here, they intersect only at this point, which is contained in blue. And it's fine over here because this red and blue here, they intersect at 2 points. This one is contained in that yellow, and this one is contained in that yellow. Okay. So this is the key property that we need. There's also a slightly stronger one, which asks that if I had something, so here this satisfied the property that I just discussed, but there's something extra that we can ask for, which is if I had something that was not in the highlighted part and something that is in the highlighted part, and I look at their common upper bounds, it should be unique. So this one doesn't have this stronger property because these two have both of those two sitting above them, and that's more than one thing. So this is saying that these two guys, they intersected at a point, at 2 different points. So their intersection's not connected. But this is fine for everything else. So this blue and this yellow have only 1 point sitting above them. Okay, so these, the left and the right guys have this stronger condition that I'm calling a TM ideal. This one is not an M ideal, and this one is an M ideal, but not a TM ideal. Okay, so these are the combinatorial conditions for having what's called an M ideal, but what I really want, so this is going to give us a single fiber bundle, and what we really want is this kind of tower of fiber bundles, this successive, like forgetting a point and then the next one and then the next one and so on. And so to get that inside the poset, what I really need is the chain of these M ideals. So I say I'm supersolvable if I have a chain of M ideals, and I'm strictly supersolvable if I have a chain of these TM ideals, the stronger condition. Okay. And this is a purely combinatorial property. So I'm saying it in the context of these intersections of these arrangements. But it makes sense for any poset that has this kind of local structure. So I said already that this guy on the left, this has the structure of what's called a geometric lattice. It doesn't necessarily have to come from an arrangement. And these guys over here kind of locally have this structure of geometric lattices. It doesn't necessarily have to come from an arrangement, but we can get this same kind of combinatorial structure and some nice combinatorial consequences of that. But what I'm interested in here is the topological consequences. Okay, so the top is a recap of those examples, and then below it is the main theorem that this M ideal is exactly what you need to get a fiber bundle. And your M ideal should be co-rank 1, so what that means is that these maximal guys should be just 1 under that, so that's going to say, that's going to give us this dimension drop by 1. And this is exactly what gives us the fiber bundle. And if we had this supersolvable, so the chain of M ideals, this is going to give us a tower of fibrations. And it's always the case the fiber is just going to be X with a few points removed. Okay. All right, another pause for questions. Yes?
Say something about the structural group of these fiber bundles.
Good question. So I might say something related to that momentarily. I think there's still a lot that we're kind of working on, but I want to give you another way to think about it, connecting it back to configuration spaces, and maybe that'll say something. So, and it's really coming from understanding what's the difference between this supersolvable and strictly supersolvable in topologically. And what's happening is in the strictly supersolvable case, so over on the right, notice that in the fiber I get one blue and one red, where it's not strictly supersolvable. This is where I got these two red punctures. So this red and the blue, they intersected at two different points. So in the fiber, I'm always going to get two red punctures. So when I'm strictly supersolvable, the punctures are all distinct. That's exactly what that having a connected intersection with the yellow guys is. And I'm going to get not distinct things, more than one puncture coming from the same guy when I'm not strictly supersolvable. So when they are distinct, what I can do is get a map to a configuration space that picks out what these punctures are. So if I had something downstairs, so downstairs what we have is here C star minus these 2 points where I have 1 and -1. And if I picked a point X that is not 1 or -1 and I look sitting above it, I have all y's except for where y equals 1 and where y equals x squared. So if I just record 1 and x squared, those two punctures, these must be distinct points because this was strictly supersolvable. So these are two distinct points in C star. And let's see, maybe I should already enlighten that. Okay. So, and I actually have, so in that case, I have a map from this arrangement complement to this configuration of 2 points. I have that fiber bundle from the very beginning that forgets this last point. And actually, this is a pullback of that fiber bundle. When I don't have distinct punctures, I can still get a map to a configuration space, but modulo this symmetric group action. Because here, I still get 3 distinct punctures, but I don't necessarily have a well-defined way of ordering those punctures because those two are coming from the same place. And really the obstruction is, I wrote here this non-trivial monodromy. So again, use your imagination. Downstairs I have C star minus a point. So in the fundamental group, I have a little loop around 0. And as I go around 0, you might see that kind of on one fiber, this guy is, say, the bottom puncture, but as I go around, it swaps place with the other red puncture. So we get this kind of non-trivial monodromy action that doesn't allow us to kind of write these 3 punctures in a nice way. But we can always write the set of those punctures and get a map to an unordered configuration space. Okay. So when you're strictly supersolvable, this is just pulling back this configuration space bundle. So a lot of these properties that you get for these configuration spaces can be pulled back to this. And this monodromy can be described in terms of braid groups as well. Okay. Let's see. And maybe just a side note, so up here, I kind of wrote an extra little bit. So we get this map to configurations of 2 points in C star. It's a pullback of this bundle from 3 points down to 2 points. But we can also map from the configuration space of C star to C. The configuration of C star to a configuration of C. Because 1 and x squared being in C star means they're not equal to 0. So I can add 0, and now I have a configuration of 3 points in C. And sitting above that, I have this fiber bundle of configurations of 4 points down to 3 points. Let's see. Right, so, and then it's a pullback of that bundle as well. Okay. Right, and this is where we really do get the I guess, right. I should have said this before I mentioned the braid groups. So this is where we can really pull back a lot of the more familiar things. I mean, right, there's, for an arbitrary x, these bundles are still not always, I mean, these configuration spaces are sometimes a little bit hard to grasp, but when x is equal to c, and we can pull that back in this toric case, we get some really nice consequences. Okay. And here's a few of them. So this configuration space bundle has a section, and it always, so for these, because X is a group, it's the ordered configuration space bundle will always have a section. There's a nice way to, and by a section, I mean, I want to go from configurations of n points to configurations of n plus 1, so I need to add a point in some nice continuous way. And I think, so when you're non-compact, you can do this with the unordered configuration space as well. You can kind of add a point that's really far away from all of the points in your configuration. So I think I wrote the hypotheses not quite well. So for C and C star, I just need supersolvable. For S1 times S1, I actually need strictly supersolvable because I need the ordered configuration space bundle. But once I have this, I can do the same argument that we did for configurations on C of looking at this long exact sequence in the homotopy groups. And I can see that these are k pi 1 because each of these, so the reason I restricted to these three is because that's when the fiber is a wedge of circles. So that's k pi 1. And so again, by induction, these guys will be k pi 1. And then when we have this section, so again, for C or C star, when you're supersolvable, or for any of these when you're strictly supersolvable, this short exact sequence on fundamental groups splits, and we get this semi-direct product structure of free groups. Okay. And for a torus, for C and C star, again, there's a lot of nice things that we can say, but here only when we're strictly supersolvable. So this is again where we don't get this monodromy, because what happens is the fundamental group does act trivially on the cohomology of the fiber when it is strictly supersolvable. This does not happen when you're only supersolvable. But this trivial action actually tells us, again, if we want to use the Serre spectral sequence or something to compute the cohomology using this fiber bundle structure, it is a best case scenario that the cohomology of the total space is the cohomology of the base tensor the cohomology of the fiber. And I wrote kind of these two examples. On the left is strictly supersolvable, where we do see this. So here, the cohomology of the top is the tensor product of the cohomology of this and the cohomology of this. So remember, this is C star minus 2 points, so it's really a wedge of 3 circles. Up here, again, C star minus 2 points, really a wedge of 3 circles. I just wrote down the Poincare polynomial, so this is, wedge of 3 circles times wedge of 3 circles. But we need this strictly because, again, this monodromy is not allowing us to break it down as this tensor product. Let's see. And you can see also the Poincare polynomial doesn't factor. Okay. All right, and one last consequence. Right, the Poincare polynomial, so when you're strictly supersolvable, the Poincare polynomial factors. So I wrote that down here. So when we're strictly supersolvable, the Poincare polynomial, if I just record the dimensions of these cohomology groups, it factors into this nice linear thing. But there's also an interesting connection to the fundamental group. So if you look at, for the lower central series of the fundamental group, and the successive quotients, then this lower central series kind of formula holds. So this was something that was observed, I guess, in the case of x equals c, but when you're looking at these toric arrangements and also strictly supersolvable, you get this same kind of relationship between the lower central series and the Poincare polynomial. And it really boils down to the fact that this is a case where you can do nice inductive arguments on the tower of fibrations, and it boils down to just checking something like this for the free group coming from the fibers. All right. And I think that's all. So thank you.